Today, you and I are going to meet the tensor algebra, the symmetric algebra, and the exterior algebra. They arise from three products: the tensor product, the wedge product, and the symmetric product. Here's the basic idea. Suppose that V is a vector space, and you have a multilinear map from V cross V into another vector space, U. You can convert that into a linear map from a different vector space that we call V tensor V. So what is V tensor V? Think of it as a black box. We're not going to define it as a set. We'll define it in terms of its property, a universal property that defines it up to isomorphism. There is a fixed multilinear map phi, such that for any multilinear map F, there is a unique linear map F squiggle from V tensor V to U. The moral, you started off with a multilinear map, and you ended up with a linear map. Now let's answer the question, what's in this space? The basis consists of formal expressions of the form Vi tensor Vj, where the Vi's form a basis for V. As an example, take R2 tensor R2. A vector in this space may look like a linear combination of these expressions, where the first vector comes from the first space, and the second vector comes from the second. Now we're only defining the space up to isomorphism, so this is a perfectly legal definition. Now we can define phi. Phi sends the tuple Vi, Vj to Vi tensor Vj. This might seem like just a notational shift, but it's actually a deep change in perspective. Instead of viewing these things as two different vectors, it's now one vector. So now our map is a linear map instead of a multilinear map. If you really want, you can define V tensor V explicitly as a set, but the construction is really hairy and not illuminating at all. This definition is a lot better because it's the one you actually use. You can generalize this to tensoring V with itself as many times as you want. This is called the tensor power of V, denoted like this. And if you take the direct sum of all the tensor powers of V, you get the tensor algebra. Now, let's look at the exterior algebra. Take a multilinear map from V cross V into another space, U. But now, suppose the map is alternating. If you swap any two entries, you pick up a negative sign. You can consider this as a linear map from the space lambda squared of V. Just like the tensor product, the space is defined by its universal property. There's a fixed map phi, such that for any alternating multilinear function from V cross V into U, you can replace it by a unique linear function from this space into U. As an example, consider the exterior power of R squared. A vector might look like this. Don't get scared by the wedge product. All it is a way to index every basis vector using basis vectors in R2. E2 wedge E1 is just negative E1 wedge E2 because it's alternating. E1 wedge E1 is just negative E1 wedge E1, so it has to be 0. So a basis of vectors in the set looks like this. In general, for the nth exterior power of V, a basis is every n tuple of basis vectors wedged together, where the indices are strictly increasing. Now let's see this applied. We know that the determinant function acts on n column vectors in Rn, and it's alternating and multilinear. We can rewrite it like this. All we're doing is replacing the commas with wedges, but now this is a linear map from lambda n of Rn to R. Better yet, both spaces have dimension 1. So the matrix of this linear map is a 1 by 1 matrix with entry 1, because that's how it acts on a basis vector. When I saw this, I was mind blown. It suddenly made sense why determinants are so important. They're the simplest alternating multilinear function on Rn. A brief aside, the exterior product is also used to define differential forms on manifolds. Eli Cartan actually defined differential forms using the exterior algebra. Speaking of that, what is the exterior algebra? You take all the lambda n's of V and you take their direct sum. Finally, let's take a look at the symmetric algebra. Here, we study multilinear maps where exchanging the order of inputs doesn't affect the answer. There's a space, S squared of V, such that for all symmetric multilinear maps F, you can replace them with a unique linear map from S squared of V to U. As an example, for the vector space S squared of R2, a vector may look like this, where the dot is called the symmetric product. E2.E1 is just E1.E2 because it's symmetric. But unlike before, E1.E1 isn't 0. So we end up with these basis elements. In general, for the nth exterior power of V, a basis is every n tuple of basis vectors where the indices are allowed to repeat. As before, the symmetric algebra is the direct sum of all the symmetric powers of V. So there you have it, the tensor algebra, the symmetric algebra, and the exterior algebra. A nice summary with a lot more proofs is found in these lecture notes, and I've put them in the description if you're interested in looking at them. If you want to test your understanding, try proving these identities. You just have to show that the dimensions of both sides are equal. Leave your ideas in the comments below. Thanks for watching. Stay safe, and I'll see you next time.